The other important factor when we are considering programs stored in the memory in case of a microprocessor based system is the instruction size, that is how many bytes an instruction occupies when it is put into the memory. So, that will determine the overall size of the program. So, depending upon the operand type, the instruction may have different sizes. Now, it will occupy different number of memory bytes. So, typically all instructions occupy 1 byte only. So, particularly that is for the opcode part. So, this every instruction has got an operation code or opcode, and that opcode is generally coded as an 8-bit data, as you know that in a microprocessor. So, we have got 256 possible opcodes that can be there. Of course, microprocessor 8085 uses much less than that, but typically, so the opcode part will occupy 1 byte. The exception is because of this immediate data or memory address. Like in some instructions, they have got an immediate data like MVI move immediate. So, that has got an immediate data, or if we are mentioning a memory address. So, basically these two type of instructions like this MVI B comma say 49 hex. So, this MVI B part, so that occupies 1 byte, and this 49 hex, this number occupies another byte. So, that way it becomes a 2 byte instruction. Similarly, this LXI instruction, for example, LXI H comma say 3523 hex. So, this will again occupy 3 bytes, because this LXI H part. So, this will take 1 byte, and this 3523. So, this is one 4 digit hexadecimal number. So, 2 hexadecimal digits can be put into 1 byte. So, total 2 bytes are needed for the hexadecimal address part itself. So, that way we can have 3 address 3 bytes. So, instructions that include immediate data use 2 bytes, one for opcode, one for the 8-bit data, and the instructions that include a memory address occupy 3 bytes, one for opcode and other 2 for the 16-bit address that we want to put. So, like this, as I have already said that MVI A comma 32. So, that way so this is the code of that instruction, like the manual of 8085, if you consult, you will see that this is the code for the MVI instruction, that is hexadecimal number. So, this is the number 32 in decimal. So, this is the opcode part. So, 3E. So, 3E is the hexadecimal number corresponding to the opcode MVI A, and then the next number should be 32. So, 32, this is the corresponding binary coding. So, this first byte is 3E in hexadecimal, second byte is 32 in hexadecimal. So, that way it is a 2 byte instruction. So, similarly, this jump instruction is an example where we have got a memory address and the instruction turns out to be a 3 byte instruction. First part is the jump. So, that opcode is C3, and then 2085. So, that is a 2 byte that will be required for the 16-bit address that we want to mention. And you notice here that this lower order byte that comes first, and then the higher order byte. So, while coding it, so we put C3 followed by 85 followed by 20. So, in first memory location we will have C3, second location it will have 85, third location it will have 20. So, when it is doing the instruction fetch, so in the first phase it will get C3, and in the successive phases it will get 85 and 20, and then it will then the processor will make a jump to that particular address. As far as addressing modes are concerned, so addressing modes actually tell like how many ways you can specify the data that an instruction will process. So, there are 4 addressing modes, like first one is the implied addressing mode, where the operand or the data is implied, like CMA complement accumulator. So, the instruction itself tells that the operation will be performed on the accumulator. So, that is the CMA implied type of operand. So, we have got immediate operand, immediate data like MVI B comma 45 hex. So, this here in the instruction itself I am telling what is the immediate value that we want to move to B. So, this 45 is the immediate value. Then we have got direct addressing. So, in direct addressing, so we directly specify some memory address like the instruction LDA 4000. So, what this instruction does is that the A register, the accumulator will get the content of memory location 4000. So, this is the LDA instruction by which you can load the accumulator, or it can be an indirect data like LDAX B. So, this means that the A register will get the content of memory location whose address is given by the pair BC. Okay. So, in the first case the LDA instruction, so we are directly specifying the address. In the second case LDAX instruction, so we are specifying the specifying via some sort of a pointer. So, BC register pair is acting as a memory pointer in this case. Okay. So, as far as the data formats are concerned, so since this is an 8-bit microprocessor, data can be represented in one of these 4 formats. It can be ASCII, so where you are just storing the characters. It can be BCD, binary coded decimal. It can be signed integer, so integer with sign, and unsigned integer. So, it does not consider a sign. So, since if the data is 8-bit, so a signed integer we can go for from -127 to -128 to +127. Then your unsigned integer can go from 0 to 255, and your this ASCII and BCD. So, they are ASCII is so 7-bit, but it is extended to 8-bit, and BCD is binary coded decimal. So, since we need 4 bits for coding one decimal number, decimal digit between 0 and 9. So, in 8-bit, so you can code 2 decimal digits. So, it is often represented as binary coded decimal format. It is important to recognize that the microprocessor deals with zeros and ones, and it deals with values as strings of bits. So, it always handles the data as string of bits, and it is up to the user to understand the meaning of what this string will correspond to. Like when you are putting it on say a set of LEDs, so it may be representing a pattern of glowing of those LEDs. If you are putting it on a say some display, then maybe it is the character that comes out of that may correspond to the ASCII number, ASCII character that you want to display. So, this way these data formats will vary. Now, for example, this accumulator, suppose the accumulator has a content 0 1 0 0 0 0 0 1. So, there are 4 ways by which you can interpret this result. So, if you are looking for an unsigned integer expressed in binary, so this is the corresponding integer number 65. If you are looking it as a BCD, okay, in binary coded decimal format, then the first 4 bits will correspond to 1 digit, and the next 4 bits will correspond to the next digit. So, it is 41. If you are looking for an ASCII character, then this 65 or this 41 hex, you know that this correspond to the ASCII letter A, the uppercase A character. So, that is the letter character A. If you are looking it as a string of zeros and ones, where 0th and the 6th bits are set to 1 and rest are all zeros. So, this may be the interpretation when we are looking it as a bit string. So, this way we can have different interpretations of this bit strings that we have stored in the microprocessor. Next, we will be looking into something like a counter. Like many a times what happens is that we need to set some counter for loading a register with some value. So, and then we can decrement that counter and put some generate some sort of repetitive action out of that. So, we initialize some register to some value, and then we use the decrement and increment instructions to decrement or increment the register, okay, that has got the value. So, DCR and INR, so these are the 2 instructions that we have for this purpose. A loop is set up with a conditional jump instruction that loops back or not, depending on whether the count has reached the termination count or not. For example, if you start with say all 0 and say that I will count up to 100. So, when after every increment the value increases by 1. So, when it reaches 100, so you can do a termination. So, you can compare whether you have reached the value 100 or not, or other way maybe you start with 100 and check for the condition that it becomes 0. So, by means of decrement instruction, so we decrement the value, and then when it comes to 0 we stop the counter. So, the overall operation is like this. First you have to initialize the counter, and then we have to have this body of the loop. We will have the body of the loop, whatever be the action that we want to do, then update the count, and then we check whether this is a final count or not. If it is so, then it comes out. If it is not, it goes back, executes the loop body once more. A sample assembly language program for implementing this loop using decrement instruction, DCR instruction is like this. We move immediate C comma 15 hex. So, for C register gets the value 15 hex, then we decrement C and jump on not 0 to loop. So, we are decrementing the value of C. So, then it will become 14 hex, 13 hex, 12 hex like that. So, till the values are not 0, the control will be coming back to this decrement instruction, and when this value becomes 0, then it comes out of the loop. So, this way this program as such, this assembly language program fragment is doing nothing more than waiting for some time. Okay. So, one way to wait for some time is by means of this NOP or NOP instruction, and other way can be by means of putting this type of loops, which are also known as delay loops. So, we put some delay into the operation of the system. So, sometimes what happens is that this delay that we produce is not sufficient, okay, because this if you are using an 8-bit register for to hold the count, then you can get a maximum delay of 255 units. Okay. So, you can calculate out of the 255 units, the delay that is produced may not be sufficient. So, when you are looking for some periodic task to be done, so at some periodic intervals we will do the operation. So, that small delay may not be sufficient. So, for that purpose what we do, we use some register pair. So, it is we use a register pair to increase the count value that is possible. Okay. So, but there is one small problem, like in the previous instruction we have seen that after this decrement C we could do jump on not 0, because when you are this DCR instruction it affects the 0 flag. So, if the content becomes 0, then this 0 flag will be equal to 0, but equal to 1. But in case of this loop pair, so what we have to do is that we have to use this DCX and INX instruction for register pair decrement and increment, and this register pair increment decrement operations, they do not affect the status flags. So, this is by the design of the 8085 processor. So, we cannot answer why is it happening like this, but this is by the design of the processor. So, if you are using this 8085 processor and you are using 16-bit count value decrementing or incrementing by DCX INX instructions, then we have to be a bit careful. So, if the loop is looking for when the count becomes 0, so we can use a trick, like what we do, we OR the content of 2 registers in the pair and then check the 0 flag like this. So, suppose we want to have a delay of this 1000 hex. Okay. So, this 1000 hex we move it to this B register pair. So, as a result the BC pair gets the value, 1000 hex, or rather this B register gets the value 10 and C register gets the value 00. So, that is the situation. Now, this DCX B instruction, so this will directly operate on this 1000 hex instruction value, and after doing this decrement by 1, the value becomes 0FFF. Okay. Then after, so then I need to check whether the content is 0 or not, but the problem is when this DCX instruction does this, so it does not affect the status flags. Okay. So, I need somehow some technique by which I can get the status flags affected and check whether the content has become 0 or not. So, for that purpose the trick that is taken is move A comma C. So, now A register gets the value of the C register, that is FF. So, this is the C register now and this is the B register now, content of B register and C register. So, A register gets the value FF, and then we do OR accumulator with B register. So, we this FF and 0F they are ORed, FF and 0F are ORed. So, when you do this OR operation, so you get the result FF, and since the but this OR instruction, so this will affect the status flags, and you know that this FF it is not affecting the, it is not equal to 0. So, the 0 flag is not set. So, this jump on not 0 condition will be true, and then it will be jumping back to this DCX instruction. So, this way we can have register pair as a as the counter value, so that we can get larger delays. So, but so far I have talked about delays, but I did not explicitly mention the time part of it. So, I just we just had a notion that there is a delay introduced that is coming in terms of this counter value that we have put into the loop. Now, how to calculate the delay part? So, if for every instruction I can know how many clock cycles it takes. So, you know that 8085 it operates at some clock frequency. For example, we can take it to operate at 2 megahertz. Okay. So, that means it will for every clock cycle what is the duration. So, 1 upon 2 megahertz. So, that is the duration for every instruction. So, so that much is the for every clock cycle. So, every cycle is like that. Now, if you for every if you look into the manual of 8085, so you will find that for every instruction its size and its number of clock cycles are mentioned. So, from there you can calculate how many clock cycles are required, and from there you can come to the time needed for executing a particular instruction. So, if for a particular program, so if we calculate the total number of clock cycles that is needed and we divide it by the frequency, so you can get the delay that will be involved in executing the program fragment. So, if you are looking at a single instruction level, for example, this MVI instruction, it has 7 T states. So, T state means each clock period. So, how much time it, so each clock period is 1 T state. Okay. So, that is 7 T states, and if we assume that this microprocessor is running at 2 megahertz, then this instruction will require 3.5 microsecond. So, this is 7 divided by 2 megahertz. So, that is 3.5 microsecond to complete. So, the MVI instruction requires about requires 3.5 microsecond, and that is exact. Okay. So, it is not dependent on any other factor. So, that way it is exact calculation. Now, if we are writing a loop like this MVIC, FFX, DCRC and JNZ loop. So, how much what is the delay that is produced? Okay. So, first this loop initiation, so that is the MVI instruction that requires 7 clock cycles. Then we have got a decrement C, again you refer to the manual of 8085 and you can find that the decrement operation it requires 4 clock cycles. So, that is 7 plus 4, and this JNZ loop, so this requires 10 clock cycles. Okay. So, so you see it is quite obvious because this MVI instruction, so it first in the first byte it will get the opcode for MVI, in the second cycle, so it will get the value FFX. So, then that is 4 plus 3, fetch always takes 4 clock cycles or 4 T states. So, 4 plus 3 7 T states. Similarly, this decrement C of instruction, so it has got only the fetch part. So, it does not have any other once it has got the instruction it will decrement it. So, that way number of clock cycles needed is 4, and this JNZ loop. So, loop is a 16 bit value. So, I need 4 clock cycles to get the JNZ part, and then 3 plus 3 clock cycles for the getting the 16 bit address part. So, total 10 T states will be needed for this JNZ instruction. So, the first instruction initializes the loop counter and is executed only once, requiring 7 T states. The following two instructions, the decrement and JNZ, so they form a loop that requires 14 T states, taken these two things together, and they are executed 255 times until C becomes equal to 0. So, from this you can calculate the time needed. So, so we need to keep in mind that in the last iteration of the loop the JNZ instruction will fail and will require 7 T states rather than 10 T states, because actually the way it executes is first it gets that JNZ part. So, JNZ and the 16 bit value. So, this JNZ, so this for the when the if you look into the manual you will find that there are two types of timing requirement. One is the loop is successful, another case the loop is failed. So, JNZ condition is false. So, if the loop is successful, in that case it requires 10 clock cycles. If the loop is a failure, then it requires 7 clock cycles or 7 T states. So, the way we should calculate is that the total delay is that we should subtract 3 t states from the total delay to get an accurate delay calculation. And to calculate the delay, so we compute the total delay is T o plus T L, where T delay is the total delay, T o is the delay outside the loop, that is the initialization of the counter and all, and T L is the delay of the loop. So, this is the delay of the loop, and T o is the sum of all these loops. So, once we do that, so we can get the actual delay part. So, what we have, so this using this formula, so we can calculate the time delay of the previous example T 0, that is the MVI instruction. So, that took 7 t states, that is the delay of the MVI, and the T L part. So, that is 14 t states were necessary, and that is repeated 255 times. So, 14 into 255 minus 3, because for the last part. So, this J and Z when it is failing. So, it takes only 7 clock cycles, not 10 clock cycles, so 3 clock cycles less. So, that way this becomes 3, 5, 6, 7 t states. So, 14 t states for the 2 instruction repeated 255 times, reduced by 3 t states for the final J and Z. So, that gives us the total time needed, and the total time needed is this is the T loop part. So, this if you say that total delay, so T delay, so T delay is going to be equal to this 3567 plus T, that is 3574 T states, and then you know depending upon the frequency of operation. So, you can calculate what is the overall time needed. So, this is I have got here 3567 plus 7 to 3574 clock cycles. So, this 3574 divided by 2 megahertz. So, if I say that I will be operating at 2 megahertz. So, this is equal to 1787 microsecond. So, that will be the total delay produced by the previous program. So, if for the so if the program is complex, then it will take more time. So, if you are using register pair as a loop counter, then what will happen? Suppose this is the program LXI B, then DCX B, move A comma C, or accumulator B and J and Z loop. So, this LXI takes 10 t states, and this part of information, as I have already said, is available from the manual. Then this DCX B instruction takes 6 clock cycles, move A comma C takes 4 clock cycles, and or accumulator B it takes 4 clock cycles, J and Z takes 10 clock cycles. Now, based on this we can calculate what is the total delay that is required. So, T outside is equal to 10 t states for the LXI instruction, T loop body. So, that is 24, because here the total size becomes 6 plus 4 plus 4 plus 10. So, total is 24. So, 24 into 4096, that is the value that I have initialized. So, 1000 hex, that is 4096 in decimal, minus 3, that is for the last clock cycle. So, I do not do this this J and Z instruction requires only 7 clock cycles, so 3 clock cycles and less. So, total is 98301 t states. So, 24 t states of 4 instructions in the loop repeated 4096 times, reduced by 3 t states for the J and Z in the last iteration. So, total time is 98301 plus 10. So, 98311. So, based on that, so you can find out what is the total delay. So, this is your 9830311 divided by 2 megahertz. So, that way it is 49, then 155.5 microsecond. So, this is the delay that will be produced by the previous instruction, previous example. Now, if we look into, if we want to produce more delay, okay, so sometimes this is not sufficient. So, we want to put some nested loop and get the delay value increased. So, how do we do this? We initialize, so we use 2 nested loops. So, there is loop 1, which is this part. So, initialize loop 1, body of loop 1, update count 1, and if it has not reached the final count, then we go back and again execute the body of loop 1. So, this is the inner loop, and then we have got another loop over and above the inner loop. So, that updates the counter 2, and then whether it has reached the final count or not. If it is not, so it will again do the body of loop 2. So, it will go like this. So, this way we can have two nested loops. So, nested loops can be easily set up in assembly language by using two registers for the two loop counters and updating the right register in the right loop. So, this body of loop 2 can be before or after loop 1. So, that can be there. So, that does not matter. So, what I mean is this body of loop 2. So, this part, so it can be put before loop 1 or it can be put after this also. So, it does not matter. Okay. So, now we can calculate what is the total delay that is required that is generated by the process. So, you see that we have got say this particular program. So, MVI B comma 10 hex, then MVI C comma. So, these are the two counters that we have, B and C are the two register pairs Now, the inner loop is consisting of the C register. So, this decrement C JNZ loop 1. So, this will be doing this inner loop, and then we have got the outer loop. In the outer loop we decrement B and JNZ loop 2. So, that way it is doing this outer loop. Now, if we consult the manual and determine the number of T states needed for different instructions. So, this is like this. So, 7 7 4 10 10 4 10. So, like that. So, these are the delays. Now, how to calculate the total delay that is produced? So, we can do it like this. So, calculation remains same, except that the formula must be applied recursively to each loop. So, start with the inner loop and then plug that delay in the calculation of the outer loop. So, that is how, because the inner loop becomes a part of the body of the outer loop, you can say. So, we start with the inner loop, calculate the time needed there and then put it into the body of the outer loop. So, for this first initialization, that MVI C comma FFX that instruction. So, MVI C comma FFX. So, that requires 7 T states. So, this is a delay for the inner loop. So, this is outer of 1 and then this is then we have got T L1. So, the loop of this inner, the loop body of this inner loop. So, these two. So, this 10 plus 4 14, and then for the last loop this JNZ will be 7 T state. So, that way it is done 255 into 14 minus 3, that is 3567 T states, 14 T states for the decrement C instruction and JNZ instructions, that is repeated for 255 times, and then minus 3 for the final JNZ instruction. Then for the outer loop, so we have got this outer loop outside the loop. So, that is 7 T states because of this MVI B instruction, and when we are computing the loop outer loop body, then it is 16 into 14 for the 14 for this part. So, outer loop has got this decrement B and this JNZ. So, this is 14 plus whatever be the delay needed for this loop 1. So, that will come. So, that is put here. So, 14 plus 3574. So, this outer loop, so that was 3567, inner loop that was 3567 plus 7. So, 3574. So, that 3574 is added and this whole thing minus 3. So, that makes it 57405 clock cycles. So, total delay is this outer delay of 7 plus 57405 T states. So, total 57412 T states. So, if we assume 2 megahertz operation, then the total delay will be about 28.706 milliseconds. So, it is significantly high when you considering a single loop at a time. So, this way we can use nested loops for generating delays within the programs for microprocessors.